Sani Ronen. Sani Ronen serves as the leader in the product group at ARB. He has over 26 years of experience in various semiconductors and systems companies. Sani's experience include expertise in phased array and airborne radars, RF and communications, accumulated from his service in microchip, microsemi, Radwin, Siemens, and the IAF. He's a bachelor's degree. He has a bachelor's degree from the electrical and computer engineering from Ben Gurion University in Beersheba, Israel, and a master's in entrepreneurship and innovation from Swinburne University of Technology in Australia. So, Sunny, the floor is yours.
Can you hear me okay?
Yep, perfect.
Excellent. Thank you, Ravi. Okay, so thank you for attending this afternoon session. The subject for today is using AI layer to transform high-resolution radar point cloud into insight for AV applications. As Ravi mentioned, my name is Sani Ronen and I work for Arbe. I would like to post my thanks to PhD Ben Rathaus, which is our director of AI, and most of the material is based on his work. A little bit about the outline. I will touch briefly about Arbe and our technology, a little bit about imaging radar versus a normal radar. I think in today's morning sessions, we heard a few challenges of the existence of data set of radar or the lack of a wide existence, and also the challenges to use the detection from existing generation of radars for extracting insights for AV. So I will show you, and I hope I can show you how our point cloud can improve this point. In addition, most of the session will be about features that are based on our high definition point cloud, like ego motion, turn rate, orientation, shape, tracking, classification, and free space mapping based on radar only. So a little bit about Arbe. So Arbe is an Israeli startup founded almost 6 years ago, growing fast. We are soon more than 100 members. Most of us are R&D, a few PhDs. And in addition to our engagement with tier ones and OEMs, we have our headquarters in Tel Aviv. We have office in the US and China. And this year we opened our German office. A little bit about the scale of our solution and what we are doing. So our product is a chipset, radar chipset, based on RF and processing ICs. We are a tier 2. And basically, what I'm showing today, most of the work is a proof of concept on the capabilities that can be built on top of our point cloud data. So a little bit about current generation of radars that were shown in a few of the videos in the morning session. So they have some limitation on azimuth resolution. Most of them do not have elevation resolution at all or very limited resolution. And as a result, they have a challenge with stationary objects. They turn to ignore them and then cause fatal accidents, as we've seen in the last few years. And also they have grating lobes and ambiguities that are resulting also in false alarms. What is causing these limitations? So basically it's the low number of RF elements. If you have an IC, most common IC, radar IC is 3x4, that is creating 12 virtual arrays. And if you can cascade a few of those, you can go to 6x8 or even 12x16, which result in 192 virtual channels, but still the functionality and the result of those sensors are very limited and they suffer from the same issues. On top of that, you need signal processing capabilities to deal with these numbers, and the off-the-shelf solutions are not that optimal for that. So as a result, those radars are used today for adaptive cruise control. They are used for autonomous emergency braking, and I put a star around that because they are still not optimal, and we see a lot of cases of false alarm, a lot of phantom braking. This is a very hot topic recently that is caused, and those radars are not really helping. So I think most of you heard that Tesla, for example, announced removing the current generation of radars, and I can relate to that. because of the low performance and the fact that the radar is not really supporting layer 2 plus functionality, layer 4 functionality, so Tesla cannot use it for their full self-drive. On the other hand, I think radar is a very meaningful sensor, and still for safety, even for safety, today's generation of radar can improve safety, and will present the next generation of radar, the ultra high resolution radar that our base is doing, and then it can really be part of the layer 2, layer 3, layer 4 AV. So a little bit on the holistic approach, the way we see it, we are not doing evolution of chipsets to have 10% improvement or 50% improvement. It's really a revolution. We are offering a totally new type of sensor. It's not similar to the current generation of radar. You can see on the top left, on the bottom left, sorry, an example of a camera view, and below it, the point cloud. You can see the color encoding is by elevation, so you can clearly see the bridge. And this is one of the challenging cases of a truck stuck under a bridge. And without elevation resolution, you might cause an accident or a phantom braking event. But here with our radar, you can see the detection of the truck, even though it's stationary. And you can also see the gap, the difference between the truck and the bridge. So clearly the high resolution of this sensor enables you to get this rich point cloud. A small teaser, I think we'll talk about it a little bit later for tracking, but just you can see the number of detections in our point cloud. These are 5 different cases of detections, and I will elaborate a little bit later, but just as a teaser, look how rich the point cloud when you have ultra high resolution. A little bit about what we do in our bay. I think, Ravi, you mentioned it in the past, what's so special about our bay. So not to get into much details, but on a nutshell, on the right side, you see today's most advanced radar technology that is doing 12 by 16 elements. So you can see cascading of 4 ICs. And on the right side, you see the virtual channels on the antenna. So when you have 12 by 16, here in this case, most of the focus is done in azimuth, and elevation, you have just few elements. So as a result, the azimuth resolution is not that great, not enough, not sufficient for the application. And the elevation is almost non-existent. It's 20 degrees resolution in elevation. On the left side, you can see our BET technology. And when we have a system of 48 by 48, 48 TX, 48 RX, and a processor unit that can process all of that, one processor. You can see on the left side the antenna structure with the TX on the blue and the RX on the red, and then the corresponding virtual array with 2,304 virtual arrays. So as a result, we gained 1 degree azimuth resolution and 1.8 elevation resolution. So coming to that, that's relatively on the RF side, but what's the challenge coming with that? So what's the reason for vendors not to do that? After you do the RF, suddenly you come to a processing channel on the processing power and the power consumption. If we look on the top left, when we look on the number of channels, the RX channels, when we have 48 channels, and when we look on the sampling rate, a few tens of thousands samples per second, and the bit size of the sample, we are getting very fast to a data rate of almost 30 gigabytes per second. And this is on the IF level, coming into the FFT machine. When we look on the FFT machine and we want to build a cube with azimuth, elevation, range, and Doppler bins, and for example, if we want to have a Doppler resolution of 0.1 meter per second, it means more than 2,000 Doppler bins. As a result, we are getting to a theoretical figure of 1.9 terabytes per second of data, which is really, really challenging for a general purpose hardware to be able to process it. On top of that, there is a requirement on the power consumption for the system to be below 20 watts. So what we've done in our bay, we have our solution that is including a hardware solution and IP. The IP is around algorithms and unique architecture that enable us to process this big cube without losing any part of the data. And as a result, we can get the real real-time native resolution-based point cloud. On top of that, the second benefit from having more channels is also on the antenna and the beam forming of the antenna, the beam width of the antenna. On the left side, you can see the number of channels helping getting, the beam width, to have a narrow beam width and have a better resolution. So the green one is built of 48 channels. The blue one on the other end is 4 channels. So you can see the resolution that we are getting thanks to having so many channels. On the right side, the additional benefit is when you have those amount of channels and you want to have a wide field of view, you are still able to use half lambda spacing on the virtual array. And this is the blue diagram. So you can see the beam on the blue side. When you are not using a half a lambda, when you don't have enough elements, so you need to use a wider spacing, and the gray one is 0.9 lambda spacing. So in this case, on top of the beam that you're intending to do, you still have a grating lobe that will cause you a lot of false alarms and challenging post-processing. So by having an optimal number of elements, we are solving the burden of the post-processing and making it simpler. In addition, what we are doing currently is native resolution. And of course, in the future, vendors can place on top of that different algorithms to further improve that. A little bit, I'll run briefly. This is a point cloud of existing generation of radar taken from YouTube. So you can see the detection that you see here. Basically very tough to get from this radar point cloud to what's happening out there. You have capability to know there is something out there. It's some type of local maxima, but really no option for insight for AV, advanced AV. If we go to the video around that, so you can see here, this is mostly a static picture, but still there are two pedestrians coming, a grandfather and a granddaughter. So they are detected as one target. The radar is not able to separate them. In addition, in every elevation, you see only one detection. There are no 2 detection per elevation. And again, because of the lack of resolution in elevation. On the other end, when you look on the point cloud that we're able to produce with our technology, you can see here as an example, this is a representation of our form factor reference design that we build around our radar technology and presented on a ROS GUI. So when you look here, you can see the coloring here is by elevation. Actually, the data is 4D data, but you can choose how to present it. Here you can see the number of detection in this scene. You can see the difference in elevation. When it's red, it's very high. Green will be a bit lower, and blue will be on the low side. So you can see the level of details. Here you can see those 2 pedestrians on the sidewalk. So you can clearly see them. You can see how many detection per person. And you can see that they are easily separated even with the naked eye, and not to mention on the AI level. A short video that will present also our point cloud. Here you can see it's a nighttime. The car is stationary. On the bore side of the car, you can see here those detection. These are the trees. On the left side, there are higher trees, so you can see that they are higher. But let's focus on the road, on the side. So we can see here on the road, the jogger and the dog. And here you can easily see them detected and separated. This scene is taken at night, but you see the light, it's quite lit. So I think it's very easy on the camera to perform. If the light condition will be a little bit on the lower side, the camera will struggle, while the radar will have the same result at nighttime as well. We can see here another pedestrian coming on the other side, and shortly we'll see 2 joggers coming on the right side. And if you can focus here on this area, you can see the joggers coming. Here, this is a single jogger. Again, very easy to detect it and probably track it. And following 2 additional 2 joggers, and again, they can be separated by the radar. Okay, so let's move to the next session. I think in this morning session, there was a session around giving the camera capability to analyze depth. So I think, again, this is one of the cartoons that I liked as a child, and it's still relevant today. You can see a corner case, and there are a few corner cases for cameras that they will not be able to perform. And I think the capability of a radar that was also discussed to have a depth perception and also to have immediate measurement of the velocity without any delay is crucial and critical for AV. So I have another example that shows this exact point. So it's a question for you. At the dead of night, you see two headlights ahead, 50 meters away, and they are approaching you fast. So what do you do? How can you tell if those two headlights are two motorcycles or one truck? Okay, so that's the question. Let's look on the radar picture. In this slide, I'm showing it the color coding by Doppler. So green means stationary and red will mean approaching. So here you can see immediately how the radar is able to detect and separate the two motorcycles. So this first case was two motorcycle, and the second case, in a minute, we'll see the second case when you'll see additional two headlights. And then the camera on the left side, you see it's blinded. It will not be able to see. See the two headlights, and the radar will be able to detect it and track it as a single object. You can see also the Doppler detections on the red color, and the radar can see it. Okay, so what's the answer for the question? The answer is, if you want to know it and you don't have a radar, you need to cross in between. If it was two motorcycles, you were able to cross. If it was a truck, that's the end of the story. So basically, a radar can save your life, and that's not a joke. So if we look on the math around this case, we can easily calculate that for 45 meters, this was the range in this case. According to the dimension of a truck and the dimension of a motorcycle, we can see what is the needed angular resolution in order to solve this scenario. And again, we see that in practice, we'll need 1 degree azimuth resolution in order to be able to separate the two motorcycles. And again, I'm not sure this is the case with today's radar technology. And with our BET technology, we do support 1 degree azimuth resolution. We will move to the next session, talking a little bit about the advanced feature based on this point cloud. So one thing is the importance of elevation, and then ego motion, how we can enable ego motion measurement, orientation, tracking, and free space mapping. Okay, so a little bit about elevation. Again, going to 4D on top of range, Doppler and azimuth, we also have very accurate elevation, and how much elevation is important. So 4 things come into mind. First of all, the ability to measure the height of an object. If it's a truck 3 meter high, or it's a motorcycle 1 meter high. So with elevation resolution, you're able to measure it. And when you get detection, you want to know if an object is drivable underneath. The third thing is you want to know if it's drivable over, if it's just a manhole or a soda can or a tire that you cannot drive over. So this information really relies on the ability to have elevation resolution. And on top of that, the ability to have accurate dynamic calculation. I think we discussed in the morning the ego motion ability and measurement, and without elevation, the measurement will not be accurate. So this is exactly the time to show you the ego velocity. So when we look on the ego velocity measurement, it's relatively a simple principle. You do a first measurement and initial guess, and you update the estimate. You need to choose some of the stationary elements in the point cloud. And again, in order to do it accurately, you need a majority of stationary objects in the scene. When having high resolution and you have a lot of detections, most of them will be stationary. So ultra high definition radar will have many stationary objects in every scene. Once you have this object, you can measure the velocity. And by the relativity principle, the velocity that you see the object coming towards you is exactly the same velocity in the other direction of the ego car. So you can measure that. In order to do that, as I mentioned, it requires also high resolution in angular, in azimuth. In addition, it's not that simple, of course. You need some brains in the algorithm. There are a lot of corner cases that you need to be aware of and deal a little bit differently. But in any case, this scenario is a bit simplified because it's only two-dimensional. You look from top view and you take only the range and azimuth. In reality, when we pick up, for example, a street light, which is elevated, we will do the range measurement. We can do the azimuth measurement, and then again, going into the azimuth resolution capability. But on top of that, there is also the elevation element that contribute to the geometrical calculation. Without this accurate elevation, your measurement will induce errors. So this is, again, a very important point for having elevation capability. In addition to that, we're also looking into turn rate measurement. And we can do that. And when we look on the turn rate omega, which is relatively linear proportional to the horizontal velocity, we will do the similar concept. So here the car is turning to the left, and actually what we will see is the stationary object moving to the right. So again, by the relativity principle, we'll look at the object drifting to the right, so we can understand that we are drifting to the left. And by calculating the velocity, we can go back and calculate the turn rate omega. So this is a little bit noisy process, but it's learnable, and also it can help calculate and the correct calibration biases, such as wrong or not accurate installation of the sensor. So we can help with that as well. I can show you two examples of this ego motion and the turn rate. So if you can look on the right side, you see the camera view, you can see the radar by a Doppler, and on the left side, you can see the triangle, the yellow triangle here, showing the turn rate and the ego velocity of the car. Again, only based on radar. Unless I stated differently, all this information is based on 100% radar. There is no post-processing based on the camera capabilities. We just project the bounding boxes only based on radar. So this is the case here. So when we look, again, the green is stationary object. We can see the car going out of the highway. And then when you look, the velocity is going down to 60 from 80. And then the turn rate, there is a slight turn to the left. And you can see the turn rate 11 degrees going to the left. And a little bit later, we are going and leveling back, and the turn rate gets back to 0. So this is one example, and a little bit a more interesting example is in roundabout. Again, this is by Doppler, and blue will mean descending, and red is approaching. And here, let's focus on the turn rate. So we are in the roundabout. Going into the roundabout, there is a slight turn to the right. You can see here going to, oops, sorry. And slight turning to the left, we see almost 25 degrees to the left. And after the roundabout, we level back again. Okay, so this is the turn rate calculation. On top of that, when we have high resolution, we can look into object orientation. And the importance of orientation is for scene understanding, and scene understanding means ability to have planning, and planning means tracking. The big advantage of radar is the zero latency. You can measure it without any latency. In the single frame, when you do the measurement, you can get immediate information on the Doppler. You don't need to do like in camera, that you need to look in different frames and calculate it on top of a few frames. Here, if you look on the middle diagram, we grayed out all the other targets, just focusing on the truck. And you can see here the different Dopplers of the truck. The truck is turning to the left. If you look on the bottom right side, you can see the spread by azimuth and then the different velocities. So this is I think quite nice. You can see the number of detections per the track. And when you have good resolution in azimuth and good Doppler resolution, you are able to place this data in an algorithm that can really draw a line in between and get the real velocity and the turn rate of the target. We have here a few more examples of the same concept. Here, this is a truck turning to the left at 65 meters. And again, you can see the same spread of detections. And here it's a mini turning to the left, very close range. Still, you can see the same Doppler spread and the ability to have the accurate orientation based on the radar. The next step is classification. So when we look at human classification, achieved normally by size and shape, and when we put it to an AI machine, we expect it to take into account microdoppler, of course. And as we all know, this is a typical task for deep neural networks. So just to show you the potential of the radar picture, the radar point cloud, we look here on 5 different cases. We can see the palm trees, a bus, a car, a person with a supermarket trolley, and just a person. And we can play a game. I will show you the point cloud resulting from those 5 scenarios placed together in 3D. And then we can look at it. And probably, I think you will be, even with your bare eye, it will be easy to detect the palm trees, the bus, the car that looks like a shoe, the pedestrian with the supermarket trolley, and the pedestrian without. So this is the potential. Today, from our point of view, classification is still work in progress. As I mentioned, our product is basically the radar technology, but still we are doing it as a proof of concept. And currently we've played a little bit with neural networks, and we have initial results. Here, these results are really initial and based also on a minimal input from the camera. This is the only case that we take some minimal input from the camera on the target size. But basically, I think this point cloud enables CNNs the ability to have a radar-based classification. Tracking. So when we look on tracking, from our point of view, tracking is taking this point cloud as a single frame and looking into information based on multiple frames. It helps for scene understanding and creating, in the end of the day, motion vectors. So in this scenario, when we did the tracking, I think there is a small surprise that you will see. 4 seconds into the movie, we can see at 70 meters some spurious detection here on elevation. Okay, so I played the video twice, so you can look into that. So you see the normal tracking capabilities, but what's nice here on this video, as I mentioned, you can see the first bridge clearly detected, and then the second bridge, you see suddenly some detections on elevation. So when we look into that, actually we see a second bridge with a train crossing almost perpendicularly to us. And this train is being detected. And because of the elevation capabilities, we are able to understand that it is done in a different elevation and not on our level. So we don't need to take any action. I'm wondering if a normal radar, as today technology that doesn't have a lot of elevation capability, what would be the action that he will take here? So one option is to emergency brake in the middle of the highway because suddenly he sees a target coming from the right side into his lane. The other option is to say, oh, the radar has a lot of false alarms, so let's ignore the radar. I think both options are very negative and not helping. So again, this to emphasize how our elevation capabilities are helping in real case scenarios. The last functionality is free space mapping. So again, this is done based on radar only. The color coding here is by elevation. On the green stuff on the camera picture is projected by the radar. Again, this is purely 100% based on radar. So as you can see, the radar, this is quite a clean scenario in the beginning. The radar is projecting the free space. And when you will have a detection, you can see that is not detected as free space around that. And one of the challenging is here going into the highway, we will turn right. And when you will notice there is a road incline. So in the first, really in the first turn, the radar is a bit concerned if to mark it as free space, because it's inclined here in this case. And now immediately understand it's an incline and it can mark it as a free space as well. And then the free space is continuing to be in between the guardrails. So this is, again, 100% based on radar. Another example here, when putting all the things together. So in this video, you can see the detections of the car, you can see the tracking, you can see the free path, the free space mapping. This is color coding by elevation. So if you look on the left side, you can see the electricity bridges of the train here marked in yellow-green. You can see 300 meters. This is almost 300 meters detection. You can see cars crossing 200, 250 meters as well. And here, for example, this truck is being detected, and you can see the size of it in the SLAM algorithm. Bridges are clearly detected. So this is, again, here another bridge that is detected in elevation. And this is all in all the sum of all the functionalities on top of our point cloud. So if I'm summarizing up everything, I hope I was able to show you the potential of our revolutionary sensor. And I think this point cloud is relatively different from the normal point cloud of today's radar. And this radar, we believe, can be part of the backbone sensors of an AV system. Relying on a camera is okay. Today's radars are not good enough, but this ultra high resolution radar can definitely contribute and enable good fusion with radar and LiDARs for AV applications. So thank you. If you have any questions, be happy to take it.
Thank you, Sani. I think we are running short of time. Maybe just one question and we can move on to the next talk. If you have any future questions, you can chat directly to Sani.
Yeah, maybe I can ask a question. Thank you, Sani, for the presentation. I'm wondering if the radar sensor also returns some amount of uncertainty or some form of uncertainty associated with the readings.
Yes, again, there are some physics phenomena like multipaths, for example, that when you have, if you have a target and you have a guardrail, so you will have multipaths. There are ways to overcome some of them. So, for example, if they have an odd number of returns, you can do it with some kind of antenna polarization. Some cases when they are, with the same number of returns, if they are even, so you cannot really do that. But again, we are trying, some of our IP is around algorithms that enable us to filter out those phenomena. Again, today it's not 100% perfect. There are still some uncertainties coming from the radar as well.
Okay, thank you.
One point, maybe you can answer me later or send me, you see my mail for the audience. If do you see value of creating a data set of this radar point cloud and using it for different researchers? If you see value in that, please give me a note or something that will be able maybe to follow up and enable it. Because again, I think when developing advanced algorithms and running them on certain point cloud may have limited results. If the point cloud is much richer, you can have better results on that. And as mentioned today, this is part of the next generation radars. So I think it's worthwhile. Okay, thank you very much.
Thank you, Sani.